Hi everyone, welcome back. I very much hope you had a nice lunch in all your various colleges. We are still waiting for one college, but I think we're going to make a start. I'm sure they're en route as we talk and sit now. We're very excited to be able to introduce another rising star of Oxford Geography. This is Dr. Neil Hart, he's a climate scientist, and Neil is going to be talking to you about from discovery to prediction, from understanding the climate to forewarning of disasters. So, Dr. Neil Hart.
So, as you'll pick up from my accent, I'm actually not from Britain originally. I think that it is some many generations back that the Harts immigrated from a little village on the road between Brighton and London and went to Cape Town in South Africa, which is where I was born and bred. I came to England in 2012 to do a postdoc, plans going back to South Africa. Things haven't worked out, and here I still am. Although family's there and we go back quite often. But what was really nice is that must have been 2016 or 17, so by that point I was here in Oxford. I looked up and I found that my geography teacher from high school was still there, still teaching, and there was about 2 years before he retired. And just got in touch with him to say, Mr. Weber, thank you so much for your lessons. The two things that I found most interesting about geography that we did in high school was about El Nino, the big warming in the Pacific Ocean. And I had actually just written a research paper about the impact of El Nino on what we'll see in a moment, cloud bands over Southern Africa. And the other thing that really got me interested was the Norwegian model of the mid-latitude cyclone. And so Cape Town is one of the only places in Africa that actually gets cold fronts and winter rainfall. And that always excited me a bit when those storms came through. And we learned a little bit about that in the geography that I'd done when I was at high school. I really enjoyed that, and I'd actually come to the UK to work on windstorms within mid-latitude cyclones, things called sting jet windstorms. So that was my first job when I came to the UK. Now I know that your curriculum for geography might not have had those things in it for what you're doing for your A-levels, but hopefully at least some of you sitting here will, some years in the future, be able to get back in touch with your high school geography teacher and say, what you taught really helped. And if not geography, it might be physics or anthropology or some other aspect of your A-levels which really had an impact, a lasting impact on you. So, quick question out of interest, who's actually doing A-level geography? Okay, a lot of people. And who's doing A-level psychology? Okay, so maybe a little bit more of the anthropology in there as well. Who's doing A-level physics or mathematics? Okay, so there's a nice mix of you here. This is to give you a bit of a flavour of the type of research that happens in this department. The type of research that actually undergraduates in this department have been involved in. I'll flag it up as that comes on. And then to bring it to bear a little bit more on your own personal lives, why you might want to pursue this if you were to study a geography degree. So the video that you've been watching in the background here is actually a climate model simulation of the clouds across the planet. And we'll get onto it a bit later, but in the tropical belt of this map, the climate model simulation is explicitly representing thunderstorms. So actually the model is representing the way that air flows and moves to produce the big thunderstorms that we see throughout the tropics. And we'll get onto that, why that's important. And what's nice about that is that that's actually an animation produced by a model that the Met Office ran. So a colleague of ours, Richard Jones, and we work very closely with the Met Office and many other international modelling centres and research organisations in the type of work we do. So it's very collaborative. In the interest of keeping that slide cleaner, I took off the whole list of collaborators at the bottom. And a lot of this work that I'm going to present comes out of not just my own work, but work that the Climate Research Lab here in Oxford has been doing. So one of the big questions for global warming is what does it actually mean for regions? So again, to gauge the audience of it, how many of you would say you have a little bit of eco-anxiety? How many of you would say you have a moderate amount of eco-anxiety? Okay, and quite a lot. Okay, so there's still a lot of hands up. What I don't want to do with this lecture is give you more cause for anxiety. It's about how we go about actually trying to solve these problems. Okay, and there's a part of it which is the physical climate science, which is more what we'll focus on here. But there's also a part of it that's very much about human behavior. And that's where psychology, anthropology, and politics, and all these sorts of things come in, because a lot of those are the dimensions which need to be looked at, even economics, in order to achieve some of the changes which we need to achieve. For myself, having grown up where I grew up and had the certain paradigm that I've ended up with, I tend to be quite a pragmatist. And so I'm like, well, there is already warming that we're committed to. Let's figure out how best to manage it. And one of the most important things then is we need to be able to diagnose what are those risks that the global warming, which is this curve that we see on the top right, this is global average surface temperature estimated from about 1870, and it's how much the planet has warmed for the global average relative to if there hadn't been any emissions of greenhouse gases. So orange here is the change in temperature, human-induced. Blue is the natural. And so these little blue spikes, drop-offs, are every time there's been a big volcanic eruption in the tropics. That tends to put lots of aerosol in the stratosphere, which cools the Earth by reflecting sunlight. And you can see everything is warmed. And in fact, when I started university, which is a little while ago now, 2003, for the first 5 years of my degree, I went from an undergraduate into master's and PhD, I wasn't interested in global warming. And the reason for it was simple, is that it was being presented in this context. And I'm like, but nobody lives in the global mean. This is really boring. I'm much more interested in weather. And so my PhD work was actually focused on these tropical, extratropical cloud bands, which are very important over southern Africa. They're actually important across the whole southern hemisphere. South America, Australia, the South Pacific. These big bands of cloud which link deep tropical convection all the way into the Southern Ocean produce a huge amount of the rain in the region, but also the extreme weather. As you'll see now, I am interested in global warming and working on that problem as well. But at the time I was studying, that didn't interest me, this did. And what we'll look at here is how these actually are more and more connected. So take note of this website. Let's see, hopefully this works. Let's give it a go. Yeah, so this is the latest IPCC. So IPCC is the Intergovernmental Panel on Climate Change. And it's where all the scientists get together to discuss the state of the art of what we know about climate change. And in the latest one, which came out in 2021, they actually made this really nice website, which means you can go and look at all of the climate change yourself if you want to. So you can choose the data set you want, which is a whole lot of different model projections. You can see, work with me, mouse. Over here, you can choose the observations, you can choose your variable, quantity, and scenario. And what you here have is just temperature and the annual temperature, how much that's changing if the planet warms by 2 degrees into the future, what that looks like regionally. And you can see that, for example, the Arctic warms a lot more than anywhere else. But there's other hotspots across the planet. The other thing you can see is that there's only a bit of hatching over here. And if you click on this down here, it says low model agreement. So this is related to the fact that the models really don't know what will happen with the Atlantic meridional overturning. If you've heard about that, you can go and watch the silly blockbuster called Day After Tomorrow if you want to. It's from a long time ago, but it's kind of fun. If we change this to be a different variable, so the planet's warming. That's what we've shown with that mean temperature. That's unequivocal. Let's change to total precipitation. And straight away we have hatching everywhere. And what this tells you is that the climate models that we currently have are really not certain about whether the planet will get will get wetter or drier across the globe. However, what this interactive thing allows you to do is to choose different baselines. So this is the pre-industrial, but let's be a bit more realistic. Let's say the climate in which your parents grew up. I'm making assumptions about how old your parents are, but let's say 1960s to 1990s. I think most of our parents were growing up in that period. And then let's change this to be, rather than annual, let's change it to be September to November. Now, straight away, you still have a lot of hatching, but if you look closely, you can see that over Southern Africa, parts of South Australia, the Amazon, and possibly into the Mediterranean, there is actually a strong model agreement of there being a particular drying. And if we look at the planet, if it gets even warmer, you can see that this gets even worse. So the Amazon and South America and Southern Africa are two areas where drying is looking to be in high agreement amongst models, and actually the Mediterranean too. And particularly in this spring period, so the Southern Hemisphere spring, September to November. Okay, so you can go and play around with that website more and look at things that are more relevant possibly for Europe or the UK. I would like to go back to this presentation. Now, both these places are places which have summer monsoons, which means most of the rain comes in the summer. So during the winter, it's cooler, never colder than 10 degrees because you're in the tropics really, but very dry. And when it comes to their spring, which is around about October or November, rain starts to fall and it goes into the core summer season of December, January, February, and that's when it is raining the most in these parts of the planet. It's much like the Indian monsoon, but this is in the southern hemisphere now. And if we focus particularly on what we call onset, so the start of these rains, you can actually see that there's about a 2-week delay in the start of those rains. So there's clearly a problem emerging here. Now, one of the things is that these events, which I studied for my PhD, tropical, extratropical cloud bands, which I've described, if you look at them particularly for how many times a cloud band occurs over a particular part of the South Indian Ocean, you can see that there's an area over the continent of Southern Africa and over Madagascar. And this is how important they are for rainfall. So upwards of 30%, and in some cases up to 60% of the rainfall comes just from these weather systems alone. And if we take a trend of the number of cloud bands in October, you can see that already in the observed period from about 1979, which is when we got good satellite data, there have been fewer of these events. Now, we have a way of identifying these automatically. So part of the PhD work I did was developing a computer vision type thing to identify these in observations and climate model data. And then working with colleagues here, we've adapted it to climate models. And actually, the work here is work from Rachel James, who did her undergraduate in this department and is now an associate professor in Bristol. And she looked at how the fact that in the CMIP5 models, so these are the models that contributed to the previous IPCC report, not the latest one, these cloud bands are in decline across the region, which is not good. So these models tell us that there's something not good happening. And we can say, well, hang on, let's think a little bit more about the details of that. So we look at the weather systems. It turns out these models can produce these weather systems similar to the observations, and they're in decline into the future. And I was actually sitting on a plane next to a woman on her way to a conference earlier this year, and her mother is in her 70s and still farming in the middle of South Africa, and rain that should arrive in November for their farm had only arrived in February this last wet season. And it was because of a decline of these weather systems. The other thing that's really important for this part of the climate, and this was actually discovered by a PhD student working here, Emma Howard. She's originally from Australia and is now back in Australia. She rediscovered something which weather forecasters knew about, but climate scientists had forgotten about, except for paleoclimate scientists, something called the Congo air boundary. So what you have here is a map of how humid the air is, and you can see that yellow shows very low humidity. So this is dry desert air. And in the Congo rainforest, the air is very moist, very humid. And there's, in the start of the season, the strong barrier between the warm air full of moisture in the Congo, this is rain, this is air that can produce rainfall, and this dry air where there's never going to be any rain. And Sophie Harvard, who did her undergraduate here, did a master's at the University of Reading, and is now back doing a DPhil, has shown that in the latest generation of models, the arrows are the change from the present to the future. This Congo air boundary, the time at which it breaks down and lets all of this moist air out over the continent to produce rainfall, the final CAB, so Congo air boundary breakdown date, is getting later. That's what the arrows mean going to the right is. And associated with that, the start of the rainy season, rainfall onset, is also getting later. Those are arrows going to the top. And what you have here is a whole set of different climate models. And even though they all disagree about how much later everything is going to be, they, on average, all have arrows that are pointing broadly somewhere towards later breakdown date, later onset. Okay. Any questions on that? Everyone sort of following? Lost? Kind of following? Okay. We keep going. Kitty Atwood, who's currently in the department as well, has also done a bunch of work looking at heat flows. And so these are particular features that form in deserts where it just gets hotter and hotter and hotter as the summer sun starts to arrive. So you don't really see them in winter, but as the summer sun starts to arrive. And she's shown that the heat flows here are increasing in frequency and their size, and this is actually probably going to play a role in delaying the start of the rains as well. So the observations say that something's happening. The models say that this is going to get worse. But the question is, are those models actually right? So the first thing is, what actually is a climate model? I've just been assuming that you might know. Basically what we do is we take the whole planet, a little bit like Minecraft, and divide it into lots of pixels. And there's pixels for every part of the planet, every part of the surface, and then those pixels actually extend in additional pixels up into the atmosphere. And so long ago, these pixels would have been very big, maybe 500 by 500 kilometers. So there might have been one box for the south of England and one box for Scotland for a whole climate model. As we've got better supercomputers, those pixels are much smaller. And so the best climate models that we have that run far into the future, those pixels are perhaps 50 kilometers by 50 kilometers now. Weather forecast models, which only have to run a few days into the future rather than centuries, they tend to have pixels that are 9 by 9 kilometers. We've also improved the accuracy, or how many levels we have in the atmosphere, which also matters for representing layers of cloud and such. And so you break Earth up into these pixels, and then for each pixel you model all the different processes that are operating in the system. So it's about rainfall, snow, moisture, energy transport and moisture evaporation from the sea, incoming solar radiation, all of these features. Now, you can imagine that if you divided Earth up into these pixels, you've made a set of approximations. And if you've made approximations, it means that your model might not be accurate. And so we've seen that the Congo air boundary might be breaking down later in these models. But in order to be sure about that, another very important part of physical geography is fieldwork. And so specifically related to that, we had a project called DryCAB, which is coming to, I think it ended actually in May this year. So that was the drying of the Congo air boundary into the future. And this was with people in this department, University of Cape Town, and working in very close collaboration with the Zambian Met Department, particularly somebody called Edson Nkonde and Felix Mbwai, who we still remain in contact with. And the point was to go into Zambia, particularly this area where the Congo air boundary forms at the beginning, and we needed to get a set of observations so we could actually understand the processes occurring when that Congo air boundary is in place and how it breaks down, in order to then have an observation of that so we could go and look if the models are doing about the same thing. And in that way, get a better idea if the models are telling us something true about the world or something just made up by mathematics. What we did is that we had in the far northwest corner a field site at a place called Kaleni Hill, or the game reserve called in Chile, and then another one in the town of Solwezi. And so this is another undergraduate from this department who's holding one of the weather balloons, and this is one at the Solwezi airport. This weather balloon, what you attach to the bottom of these weather balloons is a little instrument that measures temperature and humidity and pressure, and the balloon floats it up in the sky, measuring a profile of the atmosphere all the way up, which is important because then you're able to see how temperature and things are varying through the column and then test whether the models are doing something accurate about that. It's also a very beautiful part of the world to visit. So this is a pretty bleak outlook, and this is the fellowship project that I'm working on called First Rains. And it's really about saying, can we actually predict this years in which the onset is going to be really delayed? Like this one in South Africa where the rains arrived in February that should have arrived in November. And this is actually part of a wider initiative. So there's something that started in 2022 called Early Warnings for All. And it's about saying that we want everyone in the globe to have access to early warnings about the weather and the climate impacts that are most going to affect their lives and their livelihoods. One of the most important things, which is true both in this country, it seems that the farmers this year, the spring was incredibly dry, and so there was wheat waiting in the fields. And it had been planted in the winter, and so fortunately it had grown roots down, so it seemed as though the wheat crops in the UK had roots that were going down into the deeper layers of soil where there was still quite a lot of water left because we'd had such a wet winter. But those upper layers of soil were very dry, which meant that people that relied on grass to feed cattle had a very tough time having to buy in more feed because it wasn't raining. Fortunately, the rain has started and everything's growing. Now imagine you're in a place where your whole winter is dry and it's only when the rain starts that you can put any seed into the ground. Well, then it really matters that you know when your soil moisture, which is the orange curve, has started to rise sufficiently because of the rain, which is the blue curve, that you could go from being dry to actually planting your crops. And so we've been doing a lot of work to assess the current prediction models to see the extent to which they can actually do predictions. But we're talking about resolution. One of the things about resolution, even with pictures, and I mean, the smartphones that we have in our pockets now have remarkable pictures resolution from the cameras. But long ago, the resolution might have been something like this. You can hardly see what's happening. So if you're looking at predicting something and your pixels across Earth are very big, there's very little detail to be had. And as you increase the resolution, that's a pity, you start to see that there is actually a mountain in the background. Okay, we've lost a bunch of things. It ends up going into a much clearer picture. One of the things that's really important in the atmosphere everywhere, but particularly in the tropics, are these thunderstorms. And so, for example, this is now December. You can see there's a lot of thunderstorm activity across Africa, particularly in the southern parts and across South America. But if you move into August, so our summer here in the northern hemisphere, you can see most of this activity is actually confined to northern Africa and up into Europe. This is a period without much thunderstorms in Europe, but we certainly have these periods with a lot of thunderstorms. And when you animate that, so again, a satellite image, white is cloud, black is land, you can see that really the dominant thing is that you have these thunderstorms. And we've now just moved into a place where we actually can run models. This is now not a satellite image, this is actually a model simulation, where we can explicitly represent these thunderstorms. And so part of what we're doing is trying to see whether these particular models are better at predicting the start of the summer rains in order to have more skill. Okay, so Fran Morris actually did a physics undergraduate here in Oxford, then did her, she's from London originally, she's working with me on this project. She then went and did her PhD at the University of Leeds, and she's now back here working on a postdoc running these simulations, which is a very technically challenging task, but she's doing it incredibly well. So, coming back to why you all are here, we're working on answer this question: when will the rain start in a warming world? Because we can see this problem. So it's a particular problem which a couple of us have got our eyes into, and that's what we're trying to solve. But what are the things that you want to learn about in your degree? What are the questions that you want to answer? Does anybody know? There's always a few people that kind of have absolute clarity on what they're doing with their life. I knew that I enjoyed, yes.
Well, it's not directly related to this because I know you're focusing more on farmers and agriculture, but I think urban climatology has been like a big interest to me, particularly because, it's the urban heat island effect, and that's quite a big issue on microclimates. And I wanted to ask if there's any research being done on that.
Yeah, so within this department, not per se, but and urban heat islands are things which generally aren't introduced at the undergraduate level across the country. They're things which may well come at a graduate level and into research. But what you're talking about with urban heat islands comes to heat waves, and that's kind of one of the final things to get you thinking about this a little bit more. So I'll rush through this very quickly. When you're doing this degree, one of the first things you'll learn about is Earth system dynamics, and this happens in your first and your second year. And it's about the evolution of the planet Earth and life on Earth, to give you a really nice context for where we are. And the fact that Earth wasn't always the temperature it is now. There was a period when it was much warmer. There was a period through ice ages when it was much cooler. So we have, where was the first hominid? T-Rex and Triceratops, Diplodocus. So the period of the dinosaurs was actually ridiculously long. T-Rex did not eat Diplodocus. They didn't live at the same time. Farming. So farming is, you can see that the axes here are not continuous, but farming only really started much later on. It's a very 5,000, 6,000 years ago, first evidence of farming. And here we have kind of recent climate. So this is the period, the little ice age, when there were ice fairs on the Thames in London, because every year it froze over. So the last ice fair, I think, was, did I put it on here? No, 1979. No, like 1728, 1750. Maybe somebody else knows the history of the ice fairs. You'll also learn a lot about how the Earth system works today. And finally, what we need to prepare for across our lifetimes. And when I first saw these, I find them incredibly sobering. So I've got a 2.5-year-old and a 5.5-year-old daughter. And so when this is done in a generational setting, it becomes remarkable. So what you have here is the definition of a heat wave being the 99th percentile heat experienced at a particular location. Okay. And over here you can see that under different climate change scenarios, so this is if we did the 1.5 degrees, this is if we did 2 degrees, and this is if we did current pledges, so it's an even warmer planet. You can see that the annual area that's exposed to heat waves increases, and it really starts to increase now. It's increasing now. And so when you're doing trends, you can see that it's post-2000 that things have really started to hot up compared to before. Now what this is saying is it's saying, let's take the heat exposure that somebody born in 1960 would have had. Okay, so possibly to, so my parents were 1956. I guess your parents are probably a bit older, but the cohort that was born in 1960, and we think across their lifetime, there we go. That's their lifetime. Okay, on average. So that 1960 cohort would have X number of heat waves experienced in their lifetime, including this period, including the warming period up to about 2030. Okay. What this is saying is how much more exposed is every generation born after 1960 to heat waves. So if my aunt born here in 1960 experienced 3 extreme heat waves in her life, how many more heat waves will my daughter born in 1920 have? In 2020 have? And so if we take that, Susanna's going to have anywhere between 4 to 7 times as much exposure to heat as what my aunt born in 1960 had. Okay. Does that make sense? Or do you want me to talk through that once more? The point of this, and you can go and read this paper yourselves, the point of this is that this just shows you how the later and later you are born, the higher and higher your exposure will be to heat compared to previous generations. And this is what comes down to specifically this, the intergenerational inequities in exposure to climate extremes. If we look at a whole lot of other things, this is the same thing, and it's saying over here how much warmer the planet gets versus when you were born. And so you can see that basically everyone born after 2000 has a really large risk of being exposed to heat waves, crop failures, droughts, or river floods, far greater than their parents were. Okay, so that's your generation. But what's the strongest gradient here? The strongest gradient really is about how warm the planet gets. And so there's 2 things that needs to happen. One is our ability to live in a much hotter world needs to be dealt with, and that is context specific. So if you go to South Africa, it gets quite hot, and the people that are being most exposed are living in tin shacks. Okay. And so the way that they're going to deal with heat is going to be different because they can just go outside. Whereas in Britain, the people that are most at risk of dying from heat are the old and young. Those are the people that can't actually manage their own temperature well. And in Britain, many homes are, terrace houses where the roof has been sort of converted into an extra room, and that might be where Granny lives. And that is going to be the absolute hottest room in a house. And so, for example, it just needs to become part of culture that if there's a heat wave, Granny's bed is moved into the lounge on the bottom floor. And then it's 5 degrees cooler, and she stays fine through the heat wave. Managing these extremes is a really important thing to figure out how to deal with it. And the other thing, of course, is reducing how much greenhouse gases are emitted. And that's an incredibly challenging thing, which a lot of people are working on. So the person who gave this taster lecture last year was Miles Allen, and he started something here in Oxford. There's a big team of people working on something called net zero. So around the world, and it's about how we get our emissions to be net zero into the atmosphere. Because net zero is going to determine whether your risk of a heat wave is going to be 15 times what your parents was, or 30 times what your parents was. Okay, because that's looking up this global mean temperature change relative to the pre-industrial. And the biggest thing controlling this is how much greenhouse gases are being emitted. Okay. So I'll leave it there, and we can have any other questions that you guys wanted to ask. Yeah.
Would you say to the fact that the number of people who die from global stress it's about 10 times higher for those who die from cold temperatures rather than heat waves.
People that die from?
Like cold temperatures
Yeah.
compared to heat waves that you were talking about in a warming world. How would you do that?
I haven't myself looked much at the literature on cold. In general, we're finding that everything is getting milder, so the risk of cold is, in general, and cold outbreaks is going down somewhat. Heat waves are kind of the big emerging risk. Everything's getting milder and longer. That said, there are some parts of the world in the subtropics, Australia, parts of Southern Africa, where frost is going up actually. So, sorry, I don't have a clear answer. It's not something that I work much on. Yeah.
I just wanted to ask again, touching on the issue that you brought up with models and stuff.
Yeah.
You spoke about the need to start managing these risks a bit better. So I wanted to ask in terms of digital twins, that allow us to kind of model infrastructure and see how that will be affected by climate. What do you think their role will be in having more comprehensive models and understandings of how to mitigate these risks?
Yeah, so it's like digital twins where you're trying to create a virtual world that is able to replicate the real world as much as possible so that you can then figure out interventions that might mitigate risk. And digital twins is a word that's being used across infrastructure and climate. In some ways these are digital twins, and the reality is to have a full digital twin is nearly impossible, at least in the climate world. There's a lot of work to try and improve it, and these convective scale models is doing that work. There's absolutely a space for them. So, for example, modeling the heat structure, having high resolution digital twins of the urban environment allows you to see what happens if we go on massive tree planting drives, or if we change the color of all the roofs to be white to reflect away the sunlight rather than absorb heat. And there's already work showing that if you make surfaces white, you can make the air temperatures much cooler because you're reflecting a lot of heat rather than it being absorbed by black tar, for example. So there certainly is a space for that type of thing to figure out how to manage, both from an infrastructure perspective, but also from lots of other sorts of interventions.
Do you think that prediction is the most important part of helping some vulnerable communities cope with it, or do you think that things like other sort of responses are more important? Because I guess prediction, if it's kind of still going to happen anyway, what is the most important?
So I think prediction is really important, and the Early Warning for All initiative has come up from the fact that there's been more than a decade of something called anticipatory action. So in areas where people are incredibly exposed to climate risk or weather risk, anticipatory action allows aid organizations, for example, like Red Cross, to act in advance of the disaster. And there's actually a project that we've just had funded which is specifically looking at climate shocks on children. And so there's parts of the world, and thankfully, I think all of you in the room I would expect are shielded from this, but there's parts of the world where food insecurity is a real risk. And for Lesotho, there's preliminary results in that, but for Lesotho and Zimbabwe, there was a doubling of transactional sex amongst adolescents in a drought that happened in 23-24. And so what this is young girls your age who are going hungry, or your families are going hungry, and transactional sex, it's blunt, it's horrific, but that's the way you can get food for yourself or your communities. In advance of a drought, if the family, your families are farming families, are given a cash transfer to support your farming livelihood because you're having a drought, or you're given a different type of seed which can grow in the drought, the likelihood of you engaging in that behavior drops off a cliff. And so we're doing a bunch of research together with actually colleagues in social policy, and there's a woman here called Lucy Kluber who's done amazing work in this space to see how we can look at what climate shocks are impacting the risk of children to sexual abuse, and what interventions can be put in place or already exist. And so anticipatory action is really important in reducing that risk, and it can be anything from just warning. So, it exists already along the whole coast of India and Bangladesh. There are particular tropical cyclone evacuation centres, and there's a whole system in place where essentially the county governments are rated on how few lives are lost every time there's a tropical cyclone hitting the coast. And that works because the communication goes out saying, 5 days from now there's a risk of a tropical cyclone, get ready to leave your home. 3 days from now, we now know that the tropical cyclone is going to hit some of it in here and here, get ready. 2 years from now, okay, these districts, you're going to be hit by a tropical cyclone, move to the evacuation centres now, and then lives aren't lost. So, in that sense, there's a huge amount that can be achieved in managing risk. And there are risks that exist now that are not coming in the future. And in that case, prediction to mitigate those risks is critical now. In the same way that where on that curve will you get, how much exposed will you be in your 80s to climate risks? Well, that's where the greenhouse gas emission reduction is required. So you kind of need to be doing these things together. And that is what's happening in research and in practice. I think we probably have time for one more question. Yeah.
Are you optimistic or pessimistic in our ability to manage the impacts of climate change around the world?
I'm optimistic about that. I mean, I'm a bit of an optimist. I'm pessimistic about our ability, how much we can get greenhouse gas reduced, actually. And I mean, you can go walk around this department at this university and you will find a huge range of views. And so me personally, especially with the way geopolitics has changed now, the ability of us to work together to bring the economically, renewable energy is becoming cheaper and cheaper anyway. So like it makes economic sense, but there's more and more ideological pushback to it, which ideology is ideology, and that's where the human geography part of this degree is quite helpful. I just saw the title of Alex's talk this morning, but maybe give you a flavour of that. But in terms of that prediction, I mean, what we've seen in place already has been remarkable. And I mean, there's a huge part of anthropology as well, because you can have a perfect prediction, but like, you'll be like, I'm not going to listen. And then sitting next to you will be like, oh no, absolutely, we must leave our home. And you're like, no, but like, must get electrics in the basement's going to get flooded, I'll look after it, we're going to lose it or something. And so there's a whole lot of about psychology and anthropology about how people actually act in response to a prediction. And so there's a whole thing about how you integrate that quite like hard science number of risk into somebody's worldview and their life circumstance in a way that they take it into account and change their behavior.